All right, let's get right into it. When you think about getting oil out of the ground, you probably picture a pretty brute force operation, right? But what if I told you there's a technique that's way more about chemistry than it is about power? A way to actually convince trapped oil to just let go and flow out. Today, we're diving into the pretty amazing science of how CO2 can unlock almost every single drop of oil from a reservoir. When I say almost every drop, I am not kidding around. Under just the right conditions, this method can achieve a truly staggering level of efficiency. We're talking about this number right here, 90%. So what does 90% really mean? Well, picture this. For every 100 barrels of oil just sitting there in a section of rock, this technique has the potential to get 90 of them out. I mean, in the world of oil and gas, that number is almost unheard of. Which, of course, brings us to the big question. How on earth is that even possible? It sounds less like science and more like some kind of magic trick, but it's not magic, it's science. And it all boils down to one single, really important concept.
So, let's unpack that right now. We need to understand what miscibility is. It's basically the science of mixing perfectly. And it is the absolute secret sauce behind that incredible 90% number we just saw.
So, what is it? Put simply, miscibility is just the ability of two fluids to mix together so completely that they become one single new fluid. Think about it. There's no boundary, no separation. They just become one thing. The easiest way to get this is to think about your morning coffee. You stir in sugar and poof, it's gone. It dissolves completely, becomes part of the coffee. That's immiscible mixture. Now, the opposite of that, immiscible, that's like oil and water. You can shake that bottle all day long, but the second you stop, they're going to separate back into layers. And this right here is the whole point when it comes to oil recovery. See, deep underground, oil is stuck in these tiny pores in the rock. It's held there by something called capillary forces. You can think of them like a kind of surface tension that's just gluing the oil droplets in place. But the moment you get another fluid to become miscible with that oil, those forces just evaporate. The boundary between the oil and the other fluid is gone, so there's nothing left holding the oil back. So, okay, if getting these fluids to mix is the goal, how do you actually pull that off miles underground with two very different things, like crude oil and carbon dioxide? Well, that brings us to the really cool part, the CO2 magic trick, and how these two fluids actually become one. It's not just one thing, it's a few things happening all at once. First, you inject CO2 and it starts to dissolve into the oil. As it does that, the oil literally swells up, it gets bigger. And as the oil swells, its viscosity just plummets, which means it gets way thinner, less like honey, and more like water. And eventually, after enough CO2 gets absorbed, their properties just kind of blend together and bam, you've got full miscibility. At that point, you're not pushing oil anymore, you've created a single, super effective fluid that just sweeps everything out of the rock pores. Now, this all sounds great on paper, but scientists and engineers, they need to see the proof. So, that's what we're looking at next. It's seeing is believing, the hard data that backs all this theory up. So how in the world do you see what's happening inside microscopic rock pores miles underground? Well, you use some incredibly advanced tech. In this case, nuclear magnetic resonance imaging, or NMR. It's basically an MRI for rocks. It lets researchers literally watch this whole mixing process happen on a microscopic level, and they can see that, yep, this is exactly what's going on. Okay, so the science is solid. We can see it happening. But what about the results? What's the bottom line here? Just how much more oil does this miscible process get you compared to a non-miscible one, where the CO2 is just pushing? And honestly, the difference is just stunning. The data from these studies is crystal clear. Immiscible flooding, where you're just pushing the oil, gets you back about 33% of it. Not bad, but look at the result from miscible flooding, almost 70%. It is more than double the recovery. Think about that. That's the difference between leaving 2/3 of the oil in the ground and getting more than 2/3 of it out. But getting those amazing results isn't as simple as just pumping some CO2 into a well and calling it a day. So let's look at the final piece of this puzzle, the real-world recipe, and what it really takes to get this right. Everything we've been talking about, all of it, hinges on this one critical factor, the minimum miscibility pressure, or MMP. This is the magic number. It's the absolute minimum pressure you need in that reservoir for the CO2 and oil to even begin that mixing process. So, for an engineer to make this work, they've basically got a checklist. First, is the reservoir pressure high enough to get over that MMP threshold? If not, it's a no-go. Second, what kind of oil are we dealing with? Lighter oils with smaller molecules, they mix way more easily. And finally, you have temperature. And temperature is a tricky one because higher temps make it harder to get that miscibility, but they also help by making the oil thinner. So it's a really delicate balancing act.
So after all that science, what's the one thing you should really remember? It's this. The most important point is that this whole process isn't about brute force. It's not about just pushing oil out of the way. It's way more elegant than that. It's about fundamentally changing the oil itself, turning it into a new fluid that actually wants to flow. And that really brings us to our final thought here. This technology isn't about finding brand new oil fields. It's about being able to get so much more out of the ones we already have. Which leaves us with a pretty big question to think about. If we can actually be this efficient, what does that truly mean for the future of our existing energy resources?